Welcome, cowboys and cowgirls. This is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School. This unit is on conditional probability. This here is one of the more difficult units in AP Stats, so I hope you pay attention. Here we go. First of all, I want to introduce the idea of conditional probability. In the example below, what is the probability that a reader reads both papers given that she reads the New York Times? So that phrase, given that she reads the New York Times, is what makes this a conditional probability. We're only looking at people who read the New York Times, and among those, I guess 20% of people who read the New York Times, we want to find the probability the reader reads both. So what is the probability that they are in the green shaded region, given that they are in the 20% who read the New York Times? Here's the answer, 5% divided by 20. Okay. The numerator, 5%, is the probability that they read both papers, and the denominator, 20, is the probability they read the New York Times. Notice that the conditional probability does not equal the unconditional probability. So on the left-hand side of this equation, I have the probability of both, given they read the New York Times, and we found that to be 25%. But the probability on the right is the probability of both, and that's just simply the green region in the center, 5%. Those two do not equal each other. Here's our definition and notation. If one event has happened, the chance that another event will happen is called the conditional probability. And this is how we denote it. Probability of A given B represents the conditional probability that event A occurs assuming that B has already occurred. That's how we write it, the probability of A given B. Let's practice this using the two-way table that I've shown you before. Probability of randomly selecting a student and that student being male is 60 out of 100. That's the basically the marginal probability of being male is the column total of 60 divided by the number of students here. That's 100. Now I ask for the conditional probability. What is the probability of being male given that the student is left-handed? So if we're given that the student is left-handed, then we're only looking at these 12 people right here in this row. That's the only people we're concerned about. What is among these 12 people, what is the probability of being male? Well, it's 8 divided by 12. 8 divided by 12. So I put a little bit more of our symbolic language in here. The 8, that's the probability of being both male and left, divided by the probability of being left-handed. In this sample, are gender and handedness independent? This is a preview of what we'll be talking about in the next video. Independence. Are gender and handedness independent? Does knowing that the person is left-handed affect the probability of being male? Because if knowing one variable changes the probability of the other, then they are not independent. And that's the case here. If I know that the person is left-handed, then that increases slightly their probability of being male. So gender and handedness are not independent. Tree diagrams. Oftentimes we can use a tree diagram to solve a problem, a conditional probability, but this only works well if there are limited number of possibilities. We can't do this very well if there's a large number of possibilities. If we draw 2 cards from a deck without replacement, what is the probability that both cards are hearts? In this case, the trials are not independent. If we draw a heart on the first trial, then there are only 12 hearts left among the 51 remaining cards. So the fact that I drew a heart on the first trial changes the probability that I get a heart on the second trial. So let's just see how that works in a tree diagram. On the right-hand side there, what is the probability that the first card is a heart? Well, there's 13 hearts out of 52 cards. If the first card is a heart, then I have 12 cards that are remaining in the deck that are still hearts, and there are only 51 cards. So the probability that the second card is a heart, given the first card is a heart, is 12 out of 51. Pardon me. So the probability of getting a heart on the first trial is 13 out of 52. Probability of getting 2 consecutive hearts, 13 out of 52 times 12 out of 51. And that's a small number. If the outcome of the first event A somehow affects the probability that the second event B occurs, it is important to adjust the probability of B to reflect the occurrence of A. Here's an example. What is the probability of drawing 2 aces in a row without replacement from a deck of cards? Well, probability of drawing the first ace is 4 out of 52 because there are 4 aces in a deck of 52. But if the first card is an ace, and I'm doing it without replacement, then I only have 3 aces left in a deck of 51. So here's our general multiplication rule. It basically is a formalization of what we've just been doing. The probability that events A and B both occur can be found using this general multiplication rule. Probability of A intersect B is the probability of A times the probability of B given A. Okay, that's just what we did in our last example. What's the probability of getting, what's the probability that the first card is an ace and the second card is an ace? What's the probability that the first card is an ace times the probability that the second card is an ace given that the first card was an ace? So this here is just the formula that we applied in the last example. Now, if I take this formula right here and I rearrange it algebraically to get the conditional probability by itself, I get this equation. To find the conditional probability of B given A, I'm just going to rearrange my general multiplication rule to get this right here. Probability of B given A equals the probability of A and B divided by the probability of A. That is my conditional probability formula. Let's try it out. In this example, what is the probability that someone who reads USA Today also reads the New York Times? So I'm going to define A as the event that the person reads the USA Today, and event B is that the person reads the New York Times. I've got those probabilities, and I want to find the probability of B given A. Probability that they read the New York Times given that they read the USA Today. Okay. Here's my formula. Probability of B given A is the probability of A intersect B. That's that 5% in the middle, divided by the probability of A. That's the 35% represented by the circle on the left. So I take 0.05 divided by 30.35, and I get 0.14. That's a straightforward application of the formula that the formula for conditional probability. Now I want to talk a little bit about Bayes' theorem. Bayes' theorem. Bayes' theorem is used to revise previously calculated probabilities based on new information. It's a systematic way of incorporating new information to revise your expectations. Sometimes it is very useful to be able to flip the conditional probabilities. That is, we may know the probability of A given B, and we want to find out the probability of B given A. That's when we use Bayes' theorem. Bayes, by the way, Thomas Bayes was a Presbyterian minister back in the 1700s, and this is his work. So here's my formula for Bayes' theorem. Let A and B be two independent events. the conditional probability of A given B is given by that formula. So if we know the probability of B given A and those two marginal probabilities on the right there, probability of A and the probability of B, then we can calculate the probability of A given B. This is Bayes' formula right here. A bit complicated, but I want to show you how we use it in practice. Here's my example. What is the probability that a randomly chosen patient has a positive mammogram result? So I'm going to let event A be the person has cancer, and the event B is that the person has a positive mammogram. The first question that we will ask you in this scenario is, what is the probability of B? What is the probability of having a positive mammogram? So let me just explain how we get to this problem, because that's important to figuring out when we should that we should use a tree diagram. We want to use a tree diagram when the facts of the problem tell us one marginal. So they have to tell us one marginal, such as the probability of having cancer is 0.0035. They have to give us one marginal. And if they tell us one marginal, we can figure out the other marginal. Take 1 minus. Okay. So to get to this, we have to know one marginal and two conditionals. So suppose they give us this conditional right here, the probability of being positive given you have cancer is 0.89. Then we can calculate this right here, the probability of being negative, having a negative mammogram given that we have cancer. By the way, this is a false negative right here. That's a false negative in medical terms. Okay? So then they have to also give us a second conditional. So they have to tell us, for example, that the probability of having a positive test, given that you don't have cancer, is 0.07. By the way, this is a false positive in medical terms. So to be able to solve this type of problem, the problem has to give you one marginal and two conditionals. Okay? Now, don't be confused by the somewhat misleading medical terminology. If we say that the test is positive, that means that you do have the disease. If we say that the test is negative, that means that you do not. A bit counterintuitive, but that is the medical terminology. Don't be thrown by that. What you have to remember is we know one marginal and two conditionals. If we know that, then we can calculate all of these joint probabilities right here. These numbers here on the very right hand of the slide. Okay? What is the probability that they have cancer and are positive? Well, we take the probability of having cancer right there times the conditional probability of being positive given that you have cancer. That's the joint probability right here. Now these four numbers in this column here have to add up to 1. These numbers add up to 1 right here. These numbers in this first column, these are the marginal probabilities. The numbers here in the second column are my conditional probabilities. And the numbers right here are my joint probabilities. These have to add up to 1. So how do I figure out the probability of B having a positive mammogram? Well, I look at this row, this stem right here. How could you have a positive mammogram? Well, you could be at this stem right here with probability 0.00312, or on this stem right here with probability 0.069676. So I'm going to add this number here and that number there to get the probability of having a positive mammogram. Let's just do it. Okay? That's the symbolic language that you would use if you want to write it out like that. And here we have it. So the first product right here is the 0.0035 times 0.89. That's this joint probability. And down here is the second joint probability. I'm just going to add those. That will give me the probability of having a positive mammogram. Now, after we ask you what is the probability of having a positive mammogram? The next question the AP examiners love to ask is to find the probability that the patient suppose the patient has positive mammogram, what is the probability the patient has cancer? Okay, that's what we want to find. So we are in this world. Suppose the patient has a positive mammogram. That means I'm in this stem right here or that stem right there. That's the only two places I can be, on this stem or on that stem. And I want to find, of the people that are in this stem and on that stem, what is the probability that they have cancer? Well, these people right here, the people in this branch here have cancer. So these are the people who have cancer. And so I have to divide the percentage, this number right here, the percentage who have cancer, divided by the probability of having a positive test result. So that's the sum of 0.00312 and 0.06976. So here I've rewritten my Bayesian formula like this. The probability of A given B is equal to the probability of their intersection, that's 0.00312, divided by the probability of B. And that's what we calculated on the previous page. It's the sum of this number right here and the sum of that number right there. So there we have it. From the previous slide, we know that the probability of having a positive mammogram is that number. So the probability of having cancer, given that you've had a positive mammogram, is only 4.2%. Okay, that's a relatively small. So that's saying that only 4.2% of all people who have a positive mammogram have cancer. So the test isn't that good a test, really. And so oftentimes, the regular practice of doctors, when a woman tests positive, has a positive mammogram, is to conduct additional tests to confirm that result, because there's a lot of people who test positive who do not in fact have cancer. Those would be the false positives. So just to summarize, whenever we give you one marginal and two conditionals, like this one here and that one there, I want you to create a tree diagram exactly like this. Here's your marginals right here. Here's my conditionals right here. Multiply out all my joint probabilities right here. These should add up to 1, and then start answering the questions that we ask. That's the best way to solve these problems. Here is the other type of problem, the other fact set that we often see in this area. The CHS baseball team plays 60% of their games at night and 40% of their games in the daytime. They win 80% of all their games. If they play at night, they win 90% of their games. You read in the paper that they won yesterday's game. What is the probability that the game was played at night? Okay, well, let's just start writing down what we know here. We know that the probability that the game is at night is 60%. We know that the probability of winning is 80%. And we know that that if the game is played at night, they have a 90% chance of winning. So in this fact set, we give you 2 marginals and 1 conditional. Okay? In this scenario, if we give you 2 marginals and 1 conditional, the best way to solve this is with a Venn diagram. Okay? And always with a Venn diagram, you have to start with the inside area. Start with the inside area. Figure out what that must be. It's a little bit harder in this scenario to figure out. I'm going to do it with a two-way table, but either way, either the Venn diagram or the two-way table works. So here we go with my Venn diagram. Okay? Either the game is played in the day or night, either they win or lose. Now this first marginal, this first marginal tells me that the probability of playing at night is 0.6. So I'm going to put 0.6 down here, which tells me 0.4 has to be the probability of daytime. Probability of winning is 0.8, so I put a 0.8 right here. Okay, so then we get to this equation right here. This is where it gets a little tricky. What is the probability of winning given that they played at night? Okay, given that they played at night means that we are in this column right here. We are looking at the 60% of games that are at night. Well, if they win 90% of those games, then I have to take 90% of that 60, and that leaves me with 54 right there. Okay, 54. This is the joint probability of winning and playing at night, and it is a conditional probability of winning given that you played it at night. We calculated it from the probability of winning given you played at night being 0.9. So if I know this number right here, then I can calculate the probability of that the game was during the day and they won. I can calculate the probability the game was during the night and they lost. I can calculate the probability that the game was during the day and they lost. I can fill in every one of these blanks. And if I fill in every one of these blanks, there's not a question I can't answer with that. So the question is, what is the probability that the game was played at night? You read in the paper that they won yesterday's game. What is the probability the game was played at night? Okay, so let's put that down. The probability, we want to find the probability the game was played at night given they won. From Bayes' formula, we know that is the probability that the game was at night and they won. That's this number, 0.54, divided by the probability that they won. That is 0.8. Okay, so I get 0.54 divided by 0.8 is 0.675 or 67.5%. Okay, so, and notice this, the probability of winning given they played at night is not equal to the probability they played at night given they won. So in this fact situation, let me go back here a little bit here. In this fact situation, oops, too far. In this fact situation, the problem gives you two marginals and one conditional, such as the probability they win given they played at night, and they're going to ask you to find what is the probability they played at night given they won. They want to flip this back and forth, and for that you need Bayes' theorem, but in practice the easiest way is to use a two-way table or Venn diagram. But be very careful with it. These are two difficult problems here. That's it for today. Thank you very much.